Hello, and welcome back to CMU CS 11737, Multilingual NLP. This time I will be presenting about text classification and sequence labeling. So text classification and sequence labeling are the names for a very broad class of methods that can be used for a lot of different things. And I'm going to try to give some examples of this first going forward. So first, text classification. So text classification is the problem of given an input text X, predicting an output label Y. To give just a few examples, we might have topic classification, kind of a stereotypical example, where we take in a sentence and try to predict the topic it belongs to. So for example, I like peaches in pears might be classified into the food topic, where I like peaches in herb might be classified into the music topic, because peaches in herb is the name of a band. As you can see, this can be relatively complicated, and you can't necessarily just look directly at the words in the sentence to be able to do it effectively. We could also have language identification, where we have I like peaches in pears, and this would be classified into English, or momo to nashi ga suki, which would be classified as Japanese. Of course, this is a relatively easy example because English and Japanese use different scripts, but let's say we had other very similar languages, or maybe even dialects that we want to classify, and in this case, it would become much more difficult, especially, for example, in short informal text, like something you would see on social media. Another example is sentiment analysis. So sentiment analysis is basically the task of taking in a text and trying to determine the underlying sentiment behind the text. So for example, I like peaches in pears would be classified as positive, whereas I hate peaches in pears would be classified as negative. Notably, I wrote here that this is sentence or document level sentiment analysis, and we can also do sentiment analysis on a fine-grained level. But I won't be talking about that this particular time. And these are by far the only examples. There's many other examples of what you can do with text classification as well. Similarly, sequence labeling is also a very broad variety of methods. And for this, given an input X, we want to predict an output label sequence Y. And importantly, the output sequence Y has to be of equal length to the input sentence. This can be done for things like part-of-speech tagging. So here we have he saw two birds, and we want to calculate the part-of-speech tags as pronouns, verbs, numbers, or nouns. Also, lemmatization, he saw two birds would become he see two bird. So this is basically turning the input words into its lemma, or in other words, kind of the dictionary form that you would see in a dictionary. This is an open class sequence labeling problem because we can have essentially an infinite number of classes, but nonetheless, we're still trying to predict a label sequence of equivalent length to the input sequence. Another example is morphological tagging. So morphological tagging, basically, we take in an input and we try to predict morphological tags. And we talked a little bit about morphology in the previous class. But for example, we might want to take he and say that this is a personal pronoun, saw, say that this is in the past tense with a verb form of finite, and two is a cardinal number, birds is plural, etc. So one interesting thing about this is not picking one of a set of labels, but you can actually pick multiple labels, so it's a little bit more complicated as well. And of course, there are many more of these types of problems as well. Finally, another important thing to know about is span labeling. So span labeling is also a very broad class of methods, and in this case, we say given an input text X, we want to predict spans of that text. So these can be multi-word contiguous spans, and also labels Y. One very common example of this is named entity recognition, where we take in an input sentence like Graham Neubig is teaching at Carnegie Mellon University, and we want to predict which spans of that sentence correspond to named entities like people, places, or things. And we have an example here. Graham Neubig would be a person, and Carnegie Mellon University would be an organization. Another example is syntactic chunking, where we basically split the input sentence up into chunks, like noun phrase, verb phrase, noun phrase. Or semantic role labeling, where we take in the sentence and output things like the predicate. So here the predicate is teaching, and the arguments. So here Graham Neubig is the actor doing the teaching, and Carnegie Mellon University is the location in which the teaching is being done. And of course, there are more of these as well. So for example, I talked about document level or sentence level sentiment analysis, and we could also do sentiment analysis through span labeling, etc. So span labeling tasks are common, maybe even more common than regular sequence labeling tasks. But one reason why we talk about sequence labeling is because we can also handle span labeling tasks as sequence labeling tasks. And specifically, the way we do so is by predicting beginning in and out tags for each word in the span. So we have our spans like this. Graham Neubig is a person, Carnegie Mellon University is an organization. And we convert these into beginning of person, in person, out, 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 beginning of person, beginning of organization, in organization, in organization. And after we predict these tags on the word level, using word level sequence labeling methods, we can then convert them back into span labels. Another variety of analysis, which you could also perhaps view as a span labeling task, is text segmentation. So given an input text X, split it into segmented text Y. So a very common variety of this, tokenization, or specifically English tokenization, the way it works is relatively simple. Basically what we're doing is we're taking in an input sentence in English or other similarly easy to tokenize languages, and we split the words or tokens on punctuation or perhaps other cues that you could use to do tokenization. So in this particular case, we have a well-conceived thought exercise, and we split well and conceived on tokenization, on punctuation, and we then take the other punctuation and split it off of each of the words. And the reason why we need to do something like this is because we have quote thought here, and if all of these are treated as one word, basically our computers have no way of knowing that this is a completely different word from the word thought if we just kind of like look it up in a simple dictionary or something like this. So this is a very common variety of processing that we do for many, many different languages. In addition, we can do things like word segmentation. And word segmentation is particularly important for languages like Japanese, Chinese, or Thai, where we do not split our sentences into words according to spaces. So this is an example of kind of a noun phrase in Japanese, and it could be split up like this, so into 4 words. And actually it could also be split up in a different way without being entirely incorrect. So this way, this word means foreign, this one means people, this means voting, and this means rights. And essentially this phrase means the right of non-nationals to vote in an election. But if you split it up this other way, this becomes foreign government. So it's some sort of strange government that is ruled by carrots. So each of the words is kind of reasonable on its own, but overall, semantically, this doesn't make very much sense. So you can see that this would be rather difficult. I can know this because I'm a speaker of Japanese and could figure that out, but our systems may not necessarily be able to do so trivially. Another example is morphological segmentation. So we've talked about morphology before, and basically if we have a verb like this in Turkish, a word like this in Turkish, it can also be split in a couple ways like this. And the left way basically is dog, and then also the morphological suffix, making this plural. So this would correspond to dogs in English. And then this here is a verb for dog paddling, and the suffix for the aorist tense, which is kind of like the present tense, similar to the present tense in English. And you can see that if you split these morphemes up differently, you get dogs or dog paddle to dog paddle. So you can see that also this is non-trivial to do properly. So very often this will be done either with rule-based methods, like for example, most English tokenizers are rule-based, many morphological segmenters are rule-based, or kind of span labeling or other varieties of models. So for word segmentation in Japanese or Chinese, you would need to use a model like this. Okay. So this is a brief introduction to some of the tasks that we might want to be handling in sequence labeling or classification and how we formulate them. So I'd like to move on to the modeling part. And there's lots of stuff that could go into modeling these kinds of tasks. And of course, there's lots of tools, research on these methods. But I would like to give a very brief overview, and this will also go into our first assignment. Okay, so first, how do we make predictions? And to give kind of a very generalized way of describing how we make predictions, basically given an input X, we extract some sort of features, which I'll label H here, and predict labels Y. And for text classification, what this entails is, we have text classification and sequence labeling, and for text classification, what this entails is basically taking I like peaches, and then taking a feature extractor of some sort. This could either be kind of a heuristic feature extractor or a neural network-based feature extractor that I'm going to talk about in a bit. And we extract a single vector of features. And then from this single vector of features, we make a prediction, and that prediction could be something like a sentiment prediction for positive or negative for the entire sequence. And for word level sequence labeling, what we do is a little bit different. We basically have our feature extractor, and we extract one feature vector for each of the words in the input, and then we make one prediction for each of the words in the input. So one important thing here is, as I mentioned before, kind of the standard sequence labeling formulation assumes that there are as many outputs as there are inputs, and that makes it very conducive to doing this kind of word level feature extraction and then word level prediction. So to give a very simple example here, we could have a simple extractor, which is a bag of words. And basically, we take each input word and we look it up. And we get a one-hot vector, which is essentially a vector with only one of the elements being non-zero, all the others being zero. And this basically counts up all of the words in the sentence. And then we add them together to get our vocabulary counts for all of the words in the sentence. So this is perhaps the simplest feature extractor we could think of for something like text classification. And then from this, we then feed this into a predictor, which calculates probabilities over all of the output labels. So what do we mean by a predictor? Again, perhaps the simplest predictor that we could come up with is something that looks a little bit like this. So we feed in our feature vector that we just extracted in the last slide. We multiply it by a weight matrix. We add a bias, where the bias is kind of the probability of each of the labels on its own. And then we run it through a softmax function to get a probability vector. And the softmax function is basically a function that converts arbitrary scores into probabilities. So it looks a little bit like this. We take we exponentiate each of the scores using the natural exponent, and then we divide by the sum of all of these exponentiated scores to get a probability. And to just kind of illustrate what this looks like, basically we have arbitrary scores that can be, negative or positive, no necessity for them to be between 0 and 1 like probabilities need to be, and after we run it through this conversion, we'll get a probability vector. So this is, one way we can do classification. It's actually not necessarily a bad way to do classification for some problems. Like, for example, topic classification, whether a particular word appears in an input text is highly indicative of whether it belongs to a particular topic. However, language is not that simple. It's not just a bag of words. So to take an example from, for example, sentiment analysis, if we have the word I don't love pears, the sentence, I don't love pears, then this is, largely a negative sentence about pears. But the only really strong sentiment-bearing word here is love. And then again, if we take another sentence, there's nothing I don't love about pears. This is an extremely positive sentence, even stronger than I love pears. And this, again, the only really strong sentiment-bearing word is love. So we have no way of doing this without having a more kind of complicated method for performing these feature extraction and prediction. So what are other alternative ways we can featurize our sequence in a way that makes it conducive to making these predictions? So the first thing that we could do is something like a bag of n-grams. So basically what a bag of n-grams does is it extracts not individual words, but multiple word sequences, such as don't love, and predicts based on these. You could also make it even more complicated and do syntax-based features, such as subject-object pairs. So, for example, if you really wanted to know whether don't was connected to a positive word or a negative word, despite maybe other intervening words appearing in the sentence, you might do syntactic parsing or something like that to extract subject-object pairs or other words that were in kind of syntactic relations. However, these methods for handmade feature extraction, while they were very successful for a long time, have largely been replaced by neural networks. And what neural networks do is they basically learn how to extract features from the input text on their own without requiring this sort of handmade manipulation. And again, there's lots of different neural networks that you could be using to perform this feature extraction, including recurrent neural networks, convolutional neural networks, self-attention. And this particular time, I'm going to be talking about recurrent neural networks, but we'll also talk a little bit about the other varieties in the future. So I'm going to be giving a very brief overview for neural networks for people who have taken an NLP class that didn't go into a lot of depth or don't have very much experience with kind of deep learning or other things like this. If you already know a lot about neural networks or have used them in your own implementation or research, this part may be kind of rudimentary for you, so feel free to kind of skip over it or view it at faster speed, for example. So neural networks, basically what they are is a way for doing complicated computations. And the original motivation for them are neurons in the brain, where neurons in the brain each have synapses that connect to other neurons that allow them to kind of combine together multiple pieces of information and propagate information throughout the brain. However, in their current conception, neural networks actually are more like a mathematical object that we use to train models in an efficient method that can do things like the kind of intelligent feature extraction that I just talked about before. So because these are mathematical objects, we'd first like to link them to mathematical expressions. So if we have a mathematical expression x, we can turn this into a computation graph. And what a computation graph is basically a graph representation of this expression. And because this expression is simple, the graph is also simple. It just has a single node labeled as x. This node could be a value. It's usually going to be something like a scalar, which would be a single value, a vector, which would be, a one-dimensional vector of values, a matrix, which would be two-dimensional, or a tensor, which could be, an arbitrary number of dimensions. So essentially, this single node has a data structure within it that is one of these various values. In addition, we can do something like this. So we can add another node to the graph. And here, this node is now a new node that has an edge traveling between x and it. So an edge represents a function argument, and a node with an incoming edge is a function of that edge's tail node. So in this case, we have the transpose function. And the transpose function, because the incoming edge here is from x, we're going to be taking the transpose of x. And each variety of nodes, so in this case, this is a node corresponding to the transpose function, has to know how to compute its value. So it has to know how to compute this. And it also needs to be able to calculate the value of its derivative with respect to each argument times the derivative of an arbitrary input. So basically, that's expressed over here. And so the transpose function knows how to do this forward calculation, we call it over here, and this backward calculation of the derivative, which we call over here. And that will be important for obvious reasons in a second. So let's say we want to make our expression a little bit more complicated now. So now we have x transpose times a. So we define another input node, big A, corresponding to a matrix, and then we also have a matrix multiplication function here. And you'll notice this matrix multiplication function is a binary value, binary function taking in two inputs. The transpose was a unary function taking in a single input, and then we also have these two nodes, which are nullary, so they have no incoming inputs. We can then kind of create a more complicated graph. So we have x transpose times a times x. And what you'll notice here is this is now becoming a directed acyclic graph. So it's also taking x as input here. So it doesn't necessarily need to be in a tree structure or anything. So notably, here we're doing x transpose times a times x. But depending on what neural network library you're using, or whether this is implemented within the framework that you're currently using, you could also have a specific node for x transpose, or input 1 transpose times input 2 times input 1, if this was a function you were interested in doing, and we just need to make sure that each individual one of these calculations can follow that. So you'll notice in neural network toolkits, if there are kind of complicated functions that are done multiple times in standard neural networks, they'll also implement some of these more complicated operations as well. So then we go even a little bit further, and now we have a more complicated expression here, including, let's say, a sum at the end of the equation, and this we've expressed kind of a polynomial function. And we can also do an assignment, and when we do an assignment, basically we're labeling the node corresponding to all of the incoming functions here. So if we say y equals, that means that we're assigning node y or a name y to this node. So variable names are just labelings of nodes. So once we have this data structure of a computation graph, there's a number of algorithms that we can apply. So basically, graph construction is the creation of the graph itself. Forward propagation is basically in topological order, we compute the value of the nodes given its inputs. So what this looks like is basically we have a bunch of nullary nodes, which have no inputs. So we basically get their values for free. And then after that, we look at all of the nodes that we're able to calculate based on the inputs we have already. So that would be this transpose node or this vector multiplication node. And then we calculate that, one of those in arbitrary order. And that also opens up other nodes that can then be calculated next. And because the graph is directed in acyclic, so no cycles, that means we can just step through all of these calculable nodes in arbitrary order. So here, 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 here. until we get to the end of the graph, and we've calculated the value of the computation graph. So there's a couple other algorithms that are necessary for learning these neural networks. So basically, the most important algorithm and the reason why we bother creating this computational graph framework in the first place is backpropagation. And basically what backpropagation does is it processes examples in reverse topological order, allowing us to calculate the derivatives of the parameters with respect to the final value. This value, at training time anyway, is usually a loss function, which is a value that we want to minimize. And so, for example, this could be the negative log likelihood of a particular training data set that we want to maximize the probability of. This is a common choice, and will also be the choice that we'll use in the assignment code base. And then once we've calculated this loss function, we will want to move any parameters in the direction of this, or in the direction that minimizes this loss function. So one very common way to do this is if, let's say, W was a parameter value, L was our loss function, we use this backpropagation to calculate the derivative with respect to W, and then we multiply this by a learning rate alpha, and we remove this, or we subtract this value from W. And this process here is called stochastic gradient descent. So backpropagation, basically we start with the final value and a derivative of 1 here, and then we gradually step through in reverse topological order and calculate the derivatives with respect to all the parameters. So like, let's say A, B, and C were parameters here. We would calculate the derivatives with respect to these and then use stochastic gradient descent to try to maximize the probability based on them. So there's many different neural network frameworks that one could be using to train these. Within this class, we are going to be using PyTorch, which is a very widely used toolkit for basically learning neural networks in general, but also very widely used in natural language processing as well. So the basic process of implementing a model within this neural network framework is we create a model, so we define all the parameters that we would like to use in the model. And for each example, we create a graph that represents the computation you would like to be performing, calculate the result of that computation, and then if training, perform backpropagation and update. So for example, if we wanted to do text classification, we would be calculating the features for a particular text. We calculate the loss function with respect to the true label, and then we perform backpropagation and update for each of the examples. Okay, and so there's lots and lots of different varieties of neural nets that we could be using here. Specifically, I'm going to be talking about recurrent neural networks in this particular class. So one reason why we'd like to use recurrent neural networks is because recurrent neural networks, which I'll describe in detail in a second, are basically a tool to pass information over long distances within the sequence that they're modeling. And this is quite important for language because there are many long distance dependencies in language. So to give just one example, we could think of agreement in number or gender, etc. And to take an example from English, we have he does not have very much confidence in himself, she does not have very much confidence in herself. So we need to make sure that the gender matches between these despite the excuse me, despite the fact that we have a very long distance between them. Another example is selectional preference. So if we have the rain has lasted only as long as the life of the, we would expect essentially a ruler, probably a monarchist ruler here. And the rain has lasted only as long as the life of the, and then something here, we would expect that this would be, probably a weather phenomenon like clouds or a storm or something like this. So recurrent neural networks are essentially a variety of neural network that allows us to do this, and they're tools to remember information. So a feed-forward neural network, basically what it would be doing is it would be taking some sort of context that we would use to make a prediction, look up that in a, to turn it into a vector representation, transform it into a hidden vector that's represented by the purple here. Whereas a recurrent neural network would take context, look it up, then run through a transform, but in performing that transform, it also feeds back the previous extracted features. So what does featurizing a sequence look like? Let's say our sequence is I like these pairs. So we start out with kind of a starting vector here. Let's just assume for the time being that maybe this vector is full of all zeros. And then we feed this vector and a vector representation of a word that we look up. So basically what we would do is we would take the word I and look it up in a dictionary of all the vectors that we have and run it through an RNN to get new features here. We do a similar thing like, and importantly, when we calculate the next representation for the word like, we're also referencing the previous representation that we got from the word I. And then we do the same thing for these, we do the same thing for pairs, and by the time we've gotten all the way to the end of the sequence, we essentially have calculated the vector for all of these. We've calculated a vector that considers all of the input words. So these recurrent neural networks can be used for a bunch of things, and they can be used for both sequence labeling and text classification and sequence classification, like I described before. So if we want them to represent a whole sentence or a whole sequence, basically what we would do is we would run the representations through this neural network, get the final vector here, which is the final vector resulting from seeing all of the words, and make a prediction based on only this final vector. This can be used for things like text classification, also condition generation and other things that I'm going to be talking about in future classes, retrieval, etc. But these recurrent neural networks can also be used to represent words in context. So for example, if we wanted to calculate part of speech tags for the word I, we could use this vector for I, this vector for like, this vector for these, this vector for pairs. And importantly, when you want to make a prediction for any particular word, you will have seen that word and all of the previous words, which might give you additional context to allow you to make a kind of context-sensitive prediction. These can be used for things like sequence labeling, language modeling, which we'll talk about in a bit, and also calculating representations for parsing or other downstream tasks. So when we train RNNs, basically what we do is we take our predictions, we take our labels, we calculate a loss function for each of these predictions, sum them together, and calculate a total loss. And then after we've calculated the total loss, the unrolled graph is basically a well-formed directed acyclic graph, which we can use as a computation graph. And we take the sum of this total loss and we just backpropagate it into the rest of the graph. So notably, the parameters of the recurrent neural network are tied across time. So what do I mean by that? Basically, each of these recurrent neural network computations will have used the same parameters within the recurrent neural network, which means that when we do backpropagation, we let the gradient flow back into this recurrent neural network at each of these time steps and use the aggregated gradient over all of the time steps to train the model. And this is method that is called backpropagation through time. So to give an illustrative example of this, basically the parameters are shared between these, which means that we will have gradients flowing back into the last one, gradients flowing back into this one, into this one, into this one, etc. Now, if we actually want to use these for sequence, maybe sequence classification, but particularly sequence labeling, a simple but nonetheless important change that you can make to these is running an RNN in both directions. So basically, we concatenate the two together. We run an RNN in the forward direction, run an RNN in the backward direction, and concatenate the representations we get from both together to make our final prediction. And this is important because now when we make a prediction about any particular word, we have the ability to reference all of the other words in the sentence instead of just the previous words, for example. And we can do this again for each of the words in the sentence. Okay, so this was a very brief overview. I understand that if you know these methods already, this might have been elementary. If you don't know these methods already, then this might have gone by very quickly. If you are confused at this point, that's okay. We will have the assignment coming out, and there's also going to be some references that we will be adding online that could help you out. So if you're taking the class, please feel free to discuss with the TAs, etc. And there's also lots of tutorials online on sequence labeling that you can take a look at. So what I want to talk about next is multilingual labeling or classification data in models. So this is a class on multilingual natural language processing. So of course we would like to talk about multilingual things. And I've already given a brief overview of the types of tasks that we might want to be solving using these methods. So now I will give an idea of data in models, specifically with respect to multilingual tasks. So first, for language identification, basically language identification is one of the easier tasks to obtain data for because essentially all we need is data, textual data in that particular language, and labels given by some human annotator of what language this is in. So one very good resource for this is the LTI language identification corpus, which was made here at CMU, LTI. And this is a benchmark of 1,152 languages from a variety of free sources that you can go and download if you would like to use. And so if you want to train a language classifier, I'd certainly encourage you to use this. There's also out-of-the-box software that you can use to do language identification. Perhaps the most famous one is langid.py. So this is an off-the-shelf language ID system for 90+ languages. And there's also a nice survey of the methods that you could use here. So one caveat that I would like to give is, while I said language identification is relatively easy to get data for, it nonetheless can be quite complicated. For example, if you want to deal with code switch data that's in multiple languages, or you want to deal with Twitter data or other social network data where people speak in very informal ways and don't use good spelling, this can really throw off language identification toolkits. So despite the fact that it is relatively easy to get data for this, it can be a hard task. So then next, I'd like to talk a little bit about text classification datasets. So text classification is a very, very broad field. It covers many different types of tasks. And so I'll just give a few examples of datasets that are relatively widely used here. So one example is the MLDoc corpus, which is a corpus for multilingual document classification in 8 languages, topic classification. There's also the PAUSE-X corpus, which is a paraphrase detection corpus. And so in addition to regular text classification, there's also kind of text pair classification, which is where you feed in 2 sentences and try to make a classification. This is one example of that. Another is the cross-lingual natural language inference corpus. So this is a corpus that's very widely used in essentially kind of benchmarking multilingual models. This is textual entailment prediction, so it's also over sentence pairs, and it's trying to tell if one sentence is entailed by another sentence. Finally, cross-lingual sentiment classification. So sentiment classification is very broadly used in text classification as a whole. As a benchmark data set, it's also very useful in its own right. And there's a well-known Chinese-English cross-lingual sentiment data set that is available at this address as well. So now moving on to sequence labeling tasks. So part of speech and morphological tagging. So an extremely good resource for kind of these sort of syntactic tasks is the Universal Dependencies Tree Bank. And essentially this is not only part of speech tagging and morphological tagging, it also has other varieties of syntax as well. But within this data set, it will definitely have part of speech and morphological tags, and it has them for over 90 languages. Additionally, one contribution that this data set has made is before this data set, it was there were disparate standards across various languages about what constituted a particular part of speech or morphological tag, etc. And I think this is very reasonable. Different languages have different features, and maybe the distinctions you want to make in them are different. But that being said, it's not very conducive for cross-lingual learning or kind of accurate benchmarking of models across languages. So basically what this Universal Dependencies Tree Bank did was it converted into universal part of speech and universal morphology tag sets to make things more consistent. There are also several pre-trained models on these data sets. I would recommend Udify or Stanza, which are two varieties of models that you could be using here. So I encourage you to look them up if you're interested. Also for named entity recognition, this is another thing that has been done quite kind of broadly cross-lingually. A very famous data set for this is the Connell 2002-2003 Language Independent Named Entity Recognition data set. And this has English, German, Spanish, and Dutch human annotated data. So I think this is a very good data set, and I have gold standard in quotes here because this, at least has been annotated by humans and is usable as such. So the silver standard WikiEn data set is a entity recognition and linking data set in 282 languages. So this is very extensive, and I think that's a great thing. Unfortunately, though, the data is automatically extracted from Wikipedia using inter-page links. So that means that it's not necessarily 100% accurate all of the time. So for example, one issue here with this data set would be that these interpage links aren't always annotated, so you might be missing some entities that are actually real entities, for example. Nonetheless, being able to test your models on 282 languages is great, so I think this is another data set you should take a look at if you're interested. In addition, there's a few composite benchmarks, and what these composite benchmarks do, essentially, is they take a bunch of different tasks and try to turn them into one kind of large benchmark that you could test models on. And there were two examples of this for multilingual learning that came out recently. The first is an extreme benchmark, the extreme benchmark, which we worked on in collaboration with Google. It has 10 different tasks over 40 different typologically different languages. And there's also the XGLUE benchmark, which is a new benchmark for cross-lingual pre-training, understanding, and generation. So this is 11 tasks over 19 languages, and it also includes generation style tasks as well. So it's not just sequence labeling classification. Okay, So that brings me to the end of the class today. I hope you enjoyed it. And for the discussion in the class, we are going to do a universal dependencies comparison. So basically what I'd like you to do is download data from the universal dependencies tree bank for one language you know. It would be nice if that's one language other than English that you know, but if you are only comfortable with English, that's fine too. And one other language that you do not know and is very different from the language that you do know. And when you do this, I'd like you to look at the part of speech and morphological tags and think about what you can tell from them. For example, is the word order different between the languages, and how? Does one language have richer morphology than the other? What other things can you see about the syntax included in the languages? And starting next time, we're going to have an assignment on automatically predicting these tags for a variety of languages. Thank you very much. That's all I have for today.